Hi, this is the first in a series of recordings about the topic of interference and diffraction of light. But before talking about light, we are going to review a little bit some wave concepts. But just before going on, I'm going to point out these beautiful pictures of the butterflies and all these different colors that we see in these images. Hopefully, when we finish these sequence of recordings, we should be able to understand why do we get these colors, these beautiful colors, and this diversity in colors. Now, let's move on. Okay, just a few reminders about waves. When we talk about waves, one of the quantities we often talk about is the wavelength, which is, in other words, the length of a wave. We use the symbol lambda usually to designate wavelength, and probably an easy way to remember what a wavelength is. It's the length between two successive crests, or the distance separating two crests or two troughs, or any phase of the wave. For example, from here to the same phase here. This is a wavelength. Or from here to here. That's a wavelength. Another quantity that we usually talk about when we talk about waves is the amplitude of the wave. The amplitude of the wave is the height of the crest or the depth of the trough, which is the maximum displacement of the medium of the wave, whatever that medium is. If it is a water wave, it would be water. If it is a spring, it's going to be the spring. It's the maximum displacement from equilibrium. Like here, the equilibrium is represented by this horizontal line. The maximum displacement from that line would be the amplitude as designated as A here, or minus A, or the depth of a trough, or the height of a crest. That's the amplitude. Other quantities that we usually talk about are what we define as the frequency of a wave. The frequency of a wave, essentially, if you think about the word frequency in English, it tells us how frequent are the waves. How often do we have those waves? And then we have the period, which is the length of the wave, but instead of length in terms of distances, we are talking about time length. For example, here we are representing the wave as a function of time instead of as a function of the position. And when we look at the wave as a function of time, it's going to look the same way as the other one, as a sine function. The amplitude still is going to be the height of the crest or the depth of the trough, except the x-axis in this case is representing time as opposed to position. And the separation of two crests or two troughs or any two phases of the wave, we define that as the period. Now, before going on, I'm going to try to run a couple of simulations to illustrate what we just talked about. Okay, I need to change this to an arrow and open this one. Okay, now this particular simulation shows a lot of different things, and I'm interested only in a small part of it. So I'm going to remove the sum here. Unfortunately, I cannot remove the top screen, but I don't need it. And I'm going to make it show us a little bit more of the wave. If you notice here, we can choose what type of wave. It's a sine function, and we can tell it what to show us. The space, which gives us here the amplitude versus the position, or we can tell it to show us the time dependence, and in this case we have amplitude versus time. Another option is to try to show us both. We'll get to that in a little bit. Now, but before getting into that, let's discuss other things that we have available here. If we look at measurement tools, when we are representing the wave as a function of time, we have what's called the period tool. And the period tool, as you notice it here, it measures for us the period. And wherever I put it, I'm measuring the period. Now, if I go to space, we don't have the period tool anymore. We have a wavelength tool. And you see it does not look much different than the period tool. And that's going to be my wavelength. Wherever I put it here, the separation between identical phases of a wave is going to be the wavelength. Now, if we do the space-time, it's going to show us both. Now, if we are in space-time, this is the position here. In this case, it's given in millimeters. And if I'm standing in a particular position, I'm going to experience the wave going up and down in time, which is equivalent to what we have seen when we looked at the time dependence only. Now, when we have the space-time dependence, again, the wavelength tool is going to look what we see there. If we pause, for example, here, we can use it to measure. But the period tool is now in the form of a chronometer, of a timer, a clock. So, for example, if we step here step by step, you see how the time is increasing. Now, let's try to use that to our advantage. Look here, we have half the clock covered. Now we are at an equilibrium position of the wave here. Now let's see how much of a wave is going to pass by this point here, by the origin, when a full wave passes. That's, we had half a wave, so that's half a period. A full wave, a full period. So we use it as a timer. Okay, now the other simulation is going to show us at a more fundamental way how we create waves and what we can change. Okay, so now here we are creating waves in water waves. We are creating them by having a faucet drip water at regular intervals. Now you see the waves as they are propagating in the water. Now, if we make the faucet drip faster, that's the way we are changing the frequency of the wave. That's, if you recall, when you learned about waves, the sources of the waves, in this case the faucet, is what's going to determine the frequency of the waves. It's also going to determine the amplitude of the wave. Now, this is applicable to water waves, sound waves, light waves, all types of waves. We'll go back to the simulation a little bit later when we discuss light. We'll go back to it when we discuss light. Okay, now let's go back to our simulation. I need to get this back to pen mode. the relationship between a frequency and a period, since the time for one full oscillation is called the period, then how frequent are the waves is going to be just the inverse of that. Now, if you noticed, the wave moved by a wavelength when an amount of time equal to a period has elapsed. From here you have the relationship. Displacement is equal velocity times time. Okay, that's the wave equation. Usually we see it more of this other format where lambda is V over F, V over the frequency. That's another important equation to remember when we talk about waves.